So yet another interesting presentation. As someone who has rated a few bridges without plans, I'm excited to hear what you have to say. This is David Jauregui from New Mexico State.
Well, good afternoon. Again, my name is David Jauregui. I just changed positions. I'm Associate Dean of Academics at New Mexico State University. I was previously department head. Along with that, I'm also the director of the Bridge Inspection Program that has been going on for several decades at NMSU, where we have co-op students that do bridge inspections for the state. What I'm going to be talking about today is this project that was actually completed about 5 years ago, and it was part of a larger initiative that the DOT was facing in terms of maintaining compliance with their load ratings. So we teamed up with the New Mexico DOT and also with University of New Mexico. It started off by just doing routine load ratings of bridges for bridges with plans, and then it expanded into bridges without plans. And these are bridges that typically were owned by a city or a county, and the bridge plans may have been lost or the bridge may have just been non-engineered. And so I'm going to be focusing mainly on that, on this project. And so the one thing we did do, we looked at, talked to New Mexico, and they figured that they considered bridges without design plans to be a major issue. Most of these bridges were older, off-system bridges, as I mentioned to you before. And the major challenge rose with load rating concrete bridges without plans, and as you can imagine, it's because of the fact that we don't know what the reinforcement is, right? This is hidden, and so that was a major challenge. Bridges such as steel and timber, those are a lot easier to load rate because you can go out to a bridge site and you can measure the dimensions. You can go back to historical documentation and get a good feel for what the bridge is. And so what we looked at, we did some literature reviews, and during my time at the University of Texas, I was at the University of Texas at Austin doing bridge testing research also, and what we found was a lot of state DOTs have made headway in testing bridges, diagnostic testing and proof testing. And for those of you who are not familiar with those terms, the diagnostic testing goes along with those types of tests where you're doing a load test at a lower truck load and then calibrating a finite element model. Okay, the issue with that is that when you calibrate the model, it's at a lower load and you're extrapolating that to a higher load, right? So things like fixed bearings, okay? That's a big thing whenever you're load rating bridges. Fixed bearings can actually contribute to load distribution, but it might not be there at a higher load level. Okay, so for pre-stressed concrete, we were looking at not only using diagnostic but also proof testing, which essentially is loading at a much higher level and proving the bridge can carry a particular load. And so the tasks, first of all, was coordinating with the New Mexico DOT to gather and compile relevant information such as historical documentation, how are we going to go about doing these load tests, and the administrative side, because one of the things we really had to plan ahead for was how long were these bridge tests going to take. Several of them actually took about between 6 hours to 8 hours, so it was going to impact the traveling public. And so we had to make sure that all was in order with that, and that meant meeting with the bridge crews within the different districts and making sure we were all on the same page. The other thing we were tasked with was reviewing procedures at least 6 other state DOTs. And from our research, we found that there are certain states that are much more, I guess, developed in terms of load testing bridges. I'll give you a couple of examples, like New York, also Alabama, Florida. They had been doing load testing back since the 80s and 90s, and a lot of those bridges were already load rated based on proof tests. We reached out to all the 50 states, and we got responses from about 36 states had come back to us talking about what do they do with bridges without plans, okay? And just a few actually incorporate proof testing. And the reason is just because of the liability, right? You're actually loading these bridges to a much higher load than what they may have seen in service, okay? And so that was a big challenge for us, and we needed to make sure we were going to be doing the test correctly. We also did a literature review, as I mentioned, and then we demonstrated our procedures on a select group of bridges. So from the AASHTO manual, literature review, and state DOTs, we found that proof testing procedures were developed primarily for reinforced concrete and steel bridges. And so the general idea is that you would load test a bridge, and at times it would be, for example, Florida DOT, they have a specialized truck that you can actually position concrete blocks on a platform of a bed of a truck and load to a much higher, a very large level. And what they'll do is they'll monitor deflection, okay? And they'll stop the test whenever you start seeing nonlinearity. And a lot of the times, what's gonna cause nonlinear behavior is yielding, right? Yielding of the steel. The problem with pre-stressed concrete bridges, though, is that we don't wanna load past the concrete cracking strength. And that was the big issue for us because the bridges that we were inspecting didn't have cracks, and we didn't want to load past that serviceability limit state. So that's where we concentrated our load testing. So we did all our proof testing based on service 3, and then we extrapolated to strength 1. And I'll be illustrating this on a case study that we did. Okay, so let's talk first about what is the general procedure that we followed. Since we don't know what the reinforcement is, we estimated the amount of pre-stressing strands using Magnell diagrams. And so basically we're kind of getting an estimate just based off like what an engineer would come up with in terms of pre-stressing strand estimates. We then used a ferroscan, and we scanned the side of the beams to see what we could see inside the beams as far as reinforcement. One of the challenges we had was that whenever you have 7-wire strand in pre-stressed concrete members, the ferroscan does not work as well as if you're using, for example, or you're looking for mild reinforcement. The strand pattern itself really creates some issues in getting the results. We started off in the interest of being safe. We load tested the bridge at a diagnostic test level. We learned from the bridge behavior, and then we planned the proof test, which is basically applying as much trucks load as we could. And for our test, we used just typical dump trucks loaded with sand and gravel. And we're typically getting loads up around 70,000 pounds. So we're looking at about 68 kips, and we're putting 4 of these trucks on a bridge. Okay, and you'll see a couple of pictures where we illustrate that. And then again, we then do our proof test, make sure that we're monitoring the bridge behavior to ensure we're not gonna get any cracking. And then based off of those proof test results, we're able to load rate the structure, okay? So as far as bridges without plans, at the time of this study, which again was back in about 2016, 2017, approximately 10% of the bridges in the US had no design plans, okay? So we're looking at about 650,000 bridges located throughout the country. That's about 60 to 70,000 bridges that don't have design plans. So the ones that we have here in New Mexico that fell into this category were T-beam bridges, box beam bridges, and I-girder bridges. And you could see those listed here. I'm gonna be focusing mainly on Bridge 7701. That is the one that is, in this particular case, experienced the most damage. Particularly, you're gonna see between the tops of the beams, they had a shear key, and those were all damaged. As pointed out earlier in a talk on the UHPC retrofit of shear keys, in this case, the shear keys were not even that well designed. Okay, so it created some challenges for us when we load tested. We also did slab bridges. That's number 86 towards the bottom there, 8676. That one actually, we were able to get a very good estimate of the reinforcement and load rate the bridge using the the bridge rating program, BRR, the AASHTO program. And that one, I do have some publications at the end of this talk, so you can follow up if you're interested. All right, so let's get right into it. In terms of Bridge 7701, Bridge 7701, this was actually located in District 1, which is close to Las Cruces, New Mexico. This is a single-span pre-stressed concrete bridge, about 30 feet, and it has 9 T-beams. We have shear keys located on the top of the beams, and there's 7 keys located along the length. As pointed out earlier by Jimmy Camp and the UHPC, it kind of corresponds to like those staples that are going along the length of the girders. In this case, however, it was a very basic design. It just included 2 steel angles and then with a rebar that was welded in between those two channels. We did also a full depth inspection, found that the bridges were all in satisfactory condition, and most importantly, no full depth flexural cracks were found, and obviously we didn't want to cause any new ones, okay? So that was a big part of our plan. And so this is a kind of a couple of pictures. You could see the elevation view, but if you look on the bottom right, you see those pockets. Those are where those steel angles are located, and then there was a rebar right between the 2 steel angles. And on several of these bridges, it was broken, okay? And so at this particular study was focused on what is the load capacity of this bridge, okay? Because a lot of them are located in agricultural areas where they're going over a canal. A lot of farm equipment is being used to go over these structures. And we needed to know, what is the load capacity. So moving on to the estimate of the pre-stressing strands, we looked at coming up with an estimate based on 4 conditions, okay? So if you look at the first equation there, that is the force in the pre-stressing strand as a function of eccentricity. And that is based on the stress at the bottom of the beam at transfer. Okay, so basically we're able to come up with a force estimate with eccentricity as a function of eccentricity. The second equation, that's on the top of the beam at release, and then P3 and P4, that is going to be at the bottom of the beam at service and on the top of the beam at service. The K factor that you see there is the factor that we use for pre-stress losses. And for these tests, we actually assumed 25%. Okay, so we assumed 25% pre-stresses losses for service. Okay, and these are the resulting lines. All right, so you see P1, which is our green line. That is going to be the estimate on the vertical scale. That is 1 over the pre-stressing force. Okay, so as you go higher in that particular quantity, you're actually getting a larger pre-stressing force, okay, because you're going 1 over that value. So if we're to bind that value there, this is the region of where you have pre-stressing force with eccentricity. The top point corresponds to the lowest pre-stress and the highest eccentricity. All right, and so how do we accomplish the lowest pre-stressing force? It's by putting as much of the steel away from the center of gravity, right? So for pre-stressed concrete members, for example, if you're looking at a bulb T, you want to start filling all the rows right towards the bottom of the cross section and then moving up. Okay, so in this case, the higher the eccentricity, the lower the pre-stressing force. The bottom point represents the higher pre-stress and the low eccentricity. So really design is usually on the top point, okay, the lower pre-stress and the high eccentricity. So these are the results. We did this analysis based on HS20 loading, H20 loading, and also H15. The numbers that you see in red correspond to H20. So let's just go through that, through those numbers. If you look at the first number, the 8.56, that goes back to the previous slide. So you're looking at that low pre-stress force. If you go to the 1 over PI, that is the 8.56. So if we take an inverse of that, that means that we need about 117 kips of force, okay? And this is the amount of force you need to satisfy service 3. That was the amount that you would need. And so from there, we can then move on and come up with the area of steel required. The area of steel required was determined by dividing that force by 70% of FPU. Okay, so 70% of FPU is basically the amount of stress you can put on the cable at transfer. We come up with 0.618. And then if we divide that by 0.153, which is the area of a half-inch diameter strand, you then come up with an estimate of 4 strands. Okay, so we really just back engineered it in terms of we're saying that we need at least 4 strands. And so with that value, what we did next is we did a scan of the beam. Okay, so this is where we use the Faro scan. And if you look at plot B here, or point B, that is actually corresponding to the bottom of the beam, and that dark area right there you see is 3 strands that are bundled. Okay, so those are 3 bundled strands. As you move away from the center line and you start getting towards the end of the beam, what happens is that you have harping of the strand. Okay, so that's where you could see over here on the left, you could see the 3 strands that have that are separating. So going back to the previous slide, we were saying that we needed 4 strands, correct? As I mentioned to you before, but you know, you're going to need a little bit more than 4 strands. So it could be 2 strands in each stem. We actually went up to 3 strands, and that's what we used as the estimate. So now we have a good picture in terms of what the reinforcement is. All right, so now that we have number of strands, which we estimated to be 6 strands, we were then able to start preparing for our load test. We first determined what was the amount of moment that was going to cause cracking of the beam. Okay. We estimated what the dead load moment is just based off the size of the beam itself. And taking the difference of those two, we then figured out what is the available moment that we can apply to this bridge with a truckload. All right, and so it's about 112, you see there 113 kip feet. The truck itself in our diagnostic test was going to range between 42.4 and 92.5 kip feet. Where those numbers are coming from is that the lower number is based off of the distribution factor from the AASHTO specification. Okay, so you're basically getting that number of 112.6 times the distribution factor from AASHTO, which is shown here to be about 0.45. So that's, just think of it like each beam taking 45% of the load. We also did that estimate based on a distribution factor of 1. The distribution factor of 1 goes back to what was mentioned earlier about these shear keys. When they're broken, each individual beam is going to act independently, right? So if you're looking at a wheel line, that beam is taking load and it's not distributing any load to the adjacent beams. And that actually happened on a couple of on this load test on a couple of different beams there. This is the cross section of the beam where we put instrumentation. So all those individual circles that you see there is what we put a strain gauge. So what we wanted to do is we wanted to make sure we were monitoring each individual beam under the truckload that we were going to apply. At certain locations, we also put a strain gauge on the height of the beam. And the reason we did that was because we wanted to come up with a strain profile and estimate where the neutral axis was. That tells us also if we had a gross section or if we had a crack section. And those that actually confirmed that we did have a gross section. All right, so this is where the truckloads were positioned. If you see path 1 and path 5, you see the 2 arrows pushing down there. Those are the 2 loads from the front axle. Okay, so you have 2 wheels, 2 loads going down. So we drove the truck up onto the bridge just with the front axle. And then on pass 1 and 5 and pass 3 and 7 on the second phase, we backed the truck up. Okay, so we're gradually applying larger loads. Now, going back to the preparatory calculations, we had also estimated the amount of strain available before it cracked was 530. Okay, so we were making sure that the strain levels never exceeded that. Okay, so let's go back to the results here. You could see that we got up to about 312 kips, 312 micro strain, which was well below the 530 that would cause cracking. So we felt comfortable with this diagnostic load test that we've done. And then we moved on to the proof test. As you see here, we changed our instrumentation. We identified 4 beams that were really taking up a lot of the load because of the damaged shear keys, and we really instrumented heavily those areas. We put a strain gauge on each side of the stem, so that way we made sure that we were capturing the strain differential that we might have got across the stem there. We wanted to make sure we did not crack the beam. All right, and so here's a few pictures just showing the load test itself. The top left corner, you could see our first phase, which was 1 truck being backed up. Second phase on the top right, those are 2 dump trucks being backed up together, so that would be multi-lane loading. Bottom left would be 2 trucks back to back, and then the bottom right is 4 trucks on the bridge. Okay, this is the largest load this bridge has ever seen, and as you can see over here on the left, on phase 1, we were able to back up the truck all the way up to 14 feet. Okay, all the way to the middle. On 2 trucks back to back, we were only able to go up to 10 feet. We stopped the truck because we had already got close to the available strain. On phase 3, we were able to only get to 6.5 feet, and look at phase 4, we're only able to get to 5 feet, okay, where we started getting close to the cracking strain. All right, another thing that we made sure we did is we wanted to make sure that we did not fail the beam and shear. Okay, so there was this equation that's given in NCHRP report 549. This is simplified design procedures for pre-stressed concrete members. They come up with an estimate of VCW, which is the cracking load for the web. And we estimated that the amount of force required to crack the beam was somewhere between 27 and 42 kips. Our largest load that we applied that we were estimating is going to be about 26 kips. So that gave us some extra assurance that we weren't going to crack the beam and shear. So one thing I want to get across here is that we made several checks. We were looking at checks for flexure, looking for cracking, for shear, and all of this took a great deal of investigation to feel confident that we were not going to get anything unexpected. And going back to this, just one thing that was, we also had to console the truck drivers when they were backing up the truck, because the beams were deflecting so much that any type of gravel that was on the bridge deck was actually falling through the joints in between the beams. So there was a lot of deflection, and they were actually asking us, is it safe to continue? And we were saying, yeah, we're really confident, and we're keeping our fingers crossed behind our backs. But it was a little nerve-wracking when that was going on, because keep in mind that this was about 70 kips, so we're putting about 250,000 pounds on this bridge. All right, and so you could see here the numbers that I have in red. They are all very close to the limit that we have for available strain, right? We said 530, so we were monitoring that very closely. All right, so with that, the last thing we did was we did the final load rating. We followed the AASHTO Bridge Evaluation Manual. It gives you an equation for the target moment, which is basically the load factor times L sub R, which is the amount of moment that we would have to apply corresponding to the legal load. And then we multiply that with 1 plus impact, which we took to be 33%. So think of it like this: when you're designing, you have a load factor, you have your legal load, and then you have 1 plus impact, right? So what we're doing is we're trying to actually apply that level of load to prove the bridge can carry it, okay, through a load test. Some of the adjustment factors, we have to apply a couple of adjustment factors. One is for one lane loaded, and so for those of you who have done bridge design, you know that that's for the multiple presence factor. Whenever you have one lane loaded, there's a possibility it's going to be larger than the legal load, so that's where you get the 15%. We consider this structure to be non-redundant because of the damaged shear keys. So one beam fails, it's not going to be able to redistribute the moment. We also did an in-depth inspection. And then our daily truck traffic was less than 1,000. So with those adjustments made for one lane loaded, our load factor for one lane loaded was 1.1, and for multiple lanes loaded, it was 0.95, okay? Our final load rating factors is determined by using this equation. You have K sub naught, which is the factor considering how the proof test is terminated. And you'll get a lower value than 1 if you actually go into nonlinear behavior. Okay, we did not get into nonlinear behavior. We stopped it before we had the cracking. We reached cracking. You see that the rating factor is a ratio between what you actually applied to the bridge and what your target was. So, for example, if you have a target moment of 500 and you were only able to apply 250, that's a rating factor of half, right? As simple as that ratio. And then on the safe posting load, you have the weight of the rating vehicle times the rating factor minus 0.3 divided by 0.7. What this equation is basically saying is that you can get, for any rating factor less than 0.3, you're not going to allow any trucks on that bridge. Okay, so it's kind of a lower limit in terms of what you're going to allow to cross the structure. And these are the results. You see the one that's highlighted in red, that was the controlling case. That was one lane loaded. So we had an applied moment of 270 kip feet. We also computed what the moment was for all our legal loads, ranging from Type 3 all the way through the state vehicles of New Mexico 5A. Our rating factors range between 0.67 all the way to 1.06. Okay, so for certain legal loads, we did have to load post the structure for those particular loads. And in this case, you could see it's Type 3, the Type 3S2, New Mexico 3A, and New Mexico 5A. Now, everything that you see on this figure here is all based on the proof test. We also went ahead and went through a full bridge rating using the AASHTO BRR program, using our estimates on the pre-stressing. And what we found at the strength limit state, it was controlled by ultimate flexure, but all those ratings exceeded what we got from the proof test, so that gave us confidence that these rating values were conservative, and we were able to feel confident with the posting limits. All right, so just a summary of what we found from this. Literature review, it really provided very little guidance on proof testing of pre-stressed concrete bridges without plans. If you look at the AASHTO manual for bridge evaluation, it's really on steel bridges and reinforced concrete. There's nothing there related to pre-stressed concrete. It's valid to do service 3 limit state to actually plan your load test. Diagnostic load testing is very helpful in getting an understanding of your bridge behavior, which can then be used to properly plan your proof test. Monitoring a strain was very effective. And by the way, I've only shown one bridge test we did. We actually load tested 6 bridges, all of which were kept below the available strain and did not experience cracking. And then finally, the applied moments that we get from the AASHTO and New Mexico loads, we compared those to the target loads to come up with our safe posting level. And then it's always important to do your final rating based on strength, okay, to make sure that you are not missing anything related to the ultimate strength category. All right, with that, there's several people to thank here. We were involved with the New Mexico DOT Research Bureau. The bureau chief at the time was Scott McClure. We also worked with the Bridge Bureau, who was Raymond Trujillo, who was the state bridge engineer at the time. We also worked closely with Jeffy Hill, state bridge management engineer, and Gary Kinchin, load rating engineer, and several others from as far as the technical panel. And then the FHWA division bridge engineer was Thiet Gwynn, and then several individuals from NMSU contributed to this project. And there's just a couple of publications. I'll be happy to share those with you if you're interested, and that details a lot more of what we did as part of this project. And with that, I think I went over a little bit, but thank you for your attention.
Yeah, I think we have some time for questions. We're going into a peer breakout, so we probably have a little bit of time for questions if you want. We've got one in the back here.
Dr. Jauregui, regarding the rebar scanning, so it's been, I don't know, it's been about 6 or 7 years since you did this, and one of the problems back then was that, you know, as far as seeing, you know, those blobs, you know, exactly what they were they several strand or measuring exact size and stuff, has the technology, and that's the part of this that I think that I was most excited about, was being able to look at the rebar and detect the rebar. Has the technology improved any in the past couple of years?
Well, I think one thing that I did find is that it is extremely, it has a much higher accuracy for mild reinforcement. Okay, for pre-stressing strand, because of the configuration, the 7-wire strand, it doesn't have a consistent cross section, right? So as you move along the length of the strand, it's changing as far as what it's actually scanning.
One more thing, and of course, one of the problems was when you're scanning a slab bridge, you were able to determine the rebar at the bottom because the cover there was only about an inch. But as far as the rebar up on top, where you may have 2 inches, you had difficulty there. Has that improved any? Do you know?
Well, again, I guess I can't really speculate on that. The work that I've done, we haven't really done much more on it. But what I can tell you is that, yes, there are certain challenges, particularly for continuous span slabs, where you have a larger cover. And even more important there is, or just as important as just gaining access, right? You have to be on top of the deck to scan it, and you can't do that whenever you have traffic. It requires that you do close the bridge down in some form or fashion.
I have a question for you. If you go back to the slide that had the rating, load rating factor summary that included all the vehicles from the testing. Yeah. So Oregon has a no plans load rating procedure that I'm sure you looked at. And usually for these types of pre-stress double Ts out in rural agricultural areas, it results in a posting. Usually the SU4 is like right at the posting, and then SU5, 6, and 7 are always posted. What are the New Mexico 2, 3A, and 5A? What do those kind of correspond to in terms of weights of trucks? Oh, I see it there. I didn't see that before.
Yeah, okay. Yeah, it's there right there. Yeah, the 33.6 through the 80.6 there. Okay. As far as the weights.
Okay.
The 2 is a 2-axle, the 3 is a 3-axle tandem, and the 5A is basically your generic 18-wheeler.
Okay. So
16 tons, 23 tons, and 40 tons.
So you didn't look at the SU4, 5, and 6.
No, I think this was part of what they wanted from the DOT. We didn't look at those.
Okay.
Those legal loads.
Emergency vehicles?
For emergency vehicle, you know, in the area where we were at, that was not a typical route that they would be taking. So we didn't look at that. No, that wasn't part of the project.
Mine is quick. So you had all that instrumentation on there, and based on the configuration of the roadway there, it looks like you can't have high-speed trucks, right? They have to go fairly slow. Did you think about trying to measure impact, the actual impact that was being produced, and then you derate that as well?
Yeah, that's a good question. That would fit more under the diagnostic procedures. And so what we're trying to do is we're coming up with procedures that could be repeated. But you know, that was I think you could definitely justify a lower impact factor in this particular area. But that wasn't something we did. We were looking more at how does the target moment compare to the applied moment.
I'm going to sneak one. Could you go to the next slide, please?
Sure.
I was just curious if you took the time to reconcile the differences from BRR and your own calculations and what that was, if you were.
Oh, sure. Yeah, I'm sorry, I kind of flew through this one. But over here so these are the proof test. Is my arrow showing up there at all? Not okay. Let's see. All right. So the proof test, the service, that's from the load test, right? All those numbers are from the load test. these are load factor ratings. And so load factor are according to the AASHTO standard spec, right? And those distribution factors are based on wheel line, okay? So if you look at the differences between interior and exterior beam, those distribution factors, I mean, the load factors are exactly the same because the distribution factor according to the AASHTO standard was the same for those, the interior beam and the exterior beam. The numbers that you see in parentheses, that's assuming a distribution factor of 1, meaning that you don't have any load distribution between adjacent beams. It's just one beam taking the load. LRFR, you do have a difference in interior beams and exterior beams because you have in the code based off of LRFD, you do have a different distribution factor for interior beam and exterior beam. Okay, and we also just went ahead and ran the calculation with a distribution factor of 0.5. In all those cases, which is a very conservative assumption, they all exceeded the rating factor for the proof test. Okay, so it just gave us some confidence that we wanted to make sure that nothing from the strength limit state was lower than what we got from the proof test.
All right, David, thank you so much.
Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.